we would like to find the Fourier symbol of the Helmholtz operator. The Helmholtz operator is the following operator, let's call it H, is Laplacian plus k squared, where k is the wave number. And this is the Laplacian, is the second order elliptic differential operator. So if we have this operator acting on a function u, this is Laplacian of u plus k squared of u. I take the Fourier transform in the y direction. I take the partial Fourier transform of this partial Fourier transform in the y direction. So if the Fourier, this is the Fourier is integral, a linear integral transform. So that's gonna be Laplacian of u hat plus k squared u hat. That is the integral from minus infinity to infinity of Laplacian of u e to the minus I psi y dy plus k squared times the integral from 0 to infinity u e to minus I psi y dy. Now I can write this, I can split it into two integrals. Plus k squared integral from minus infinity to infinity u e to minus I psi y dy. Here this operator, we take the partial derivative with respect to x, the differential is dy, so this can commute the operator. So I have second partial derivative with respect to x of the integral from minus infinity to infinity u e to the minus I psi y dy, plus this one, plus k squared integral minus infinity to infinity u e to minus xi y dy. And then I have to do the following. So it's gonna be minus the integral from minus, I do integration by parts here, minus infinity to infinity of the first partial derivative with respect to y, and I take the partial derivative with respect to y of this component here, of this term here. If I take the derivative of this one, it's gonna pull outside the minus xi, with a minus becomes a plus, plus xi, integral minus infinity to infinity, uy e to the minus xi y dy. Now I can do again integration by parts here. So if I do integration by parts, I'm going to have a minus with a minus because the derivative moves to the other guy here, plus ixi squared, integral from minus infinity to infinity, e to minus xiy dy. This guy here is u hat plus k squared u hat. Ixi squared is I to the power of 2 is minus 1 minus xi squared of u hat. So that's partial square u partial x squared u hat plus k squared minus xi squared u hat. Or I can do one more step. I rewrite this term underneath. I can take a minus 1 common factor, and that's going to be xi squared minus k squared of u hat. And this I can write it in this way. U hat. So my symbol, let's call it t, is partial derivative, second partial derivative with respect to x, minus xi squared minus k squared, acting on the function u hat, which is the u hat is the Fourier transform of u in the y, partial Fourier transform in the y direction. So that's t depending on xi and k. That's my operator. So if I take how this operator become is second derivative with respect to x. So when xi is equal to k, then you end up with this second order differential operator. If xi is minus k, again you get the same. Otherwise you just get the operator back if xi is different than from plus or minus k. One more choice, if k is equal to 0, you have a second derivative with respect to x. That's my operator, minus xi squared, for k equal to 0 and xi different from 0. And this is basically when you take this is the Fourier transform of the Laplacian operator in the y direction. It's a linear operator, so if I take t u hat, what I get is the following: minus xi squared minus k squared u hat. Then this operator hits the u hat is second derivative, partial derivative with respect to the variable x, minus psi squared minus k squared of u hat. It's an interesting problem. We use the Fourier transform in many cases to solve partial differential equations. So basically, if you have this partial differential equation, which is the Helmholtz pure Helmholtz equation, you can transform it using the Fourier transform in the y direction. So you get this ordinary differential equation, basically. You get this ordinary differential equation that you could solve. And p of lambda is lambda squared minus xc squared minus k squared. And you can write as lambda squared minus xc squared minus k squared square root squared. Lambda minus this quantity here is a difference of two squares. So lambda plus is a square root of xi squared minus k squared, and lambda minus is minus the square root of xi squared minus k squared. So my general solution, u hat is a coefficient c1 e to the lambda plus of x times x plus c2 e lambda minus x. So if xi is bigger than k, then this quantity is going to be a real number. So I have this solution, u hat equals c1 e to the lambda plus x plus c2 e to the lambda minus x. Otherwise, if xi is less than k, then I can write lambda plus in the following way: I square root of k squared minus xi squared, and lambda minus I square root of k squared minus xi squared. So there is going to be u hat equals c1 e to lambda plus x plus c2 e to lambda minus x. So basically it takes the following form: c1 e to the power of 0 x cos square root of k squared minus xi squared of x plus c2 e to the 0 x sine square root of k squared minus xi squared x. So these are my two solutions. In case that xi, the Fourier frequency in absolute value, is bigger than the wave number k, then I have this solution. In case that the wave number is bigger than the Fourier frequency, I have this solution here. So I'm gonna write it more clearly. So in case that Xi is bigger than k. U hat is C1 e to the lambda plus x plus C2 e to the lambda minus x, where lambda plus and lambda minus are real numbers. Otherwise, U hat is C1 cos of square root of k squared minus xi squared x plus C2 sine square root of k squared minus xi squared times x. It's a very difficult problem, the Helmholtz problem, to solve due to the oscillating nature and due to the involvement of this wave number k, where k is omega over c. Omega is 2 pi f and c equals lambda times f, and that is 2 pi over lambda, where lambda is the wavelength.